Math and Beats video time. This video, we are going to introduce the derivative function conceptually, and that means we got to get started here. So let's go ahead and take a look at what we're getting into. So the derivative function. All right, so in the previous two videos, we went ahead and revisited the topic of the slope of a tangent line. And then we also started looking at alternative notation for the slope of the tangent line. Right? We had the slope of the tangent line was defined by a limit. And in particular, we were looking at the slope of a tangent line at a specific place for a function y is f of x, right? And that specific location was a fixed point here, some location on the graph, some point a comma f of a. We say, let's go to this point a comma f of a on the graph, and let's talk about the slope of the tangent line there, assuming it exists. However, in this video, hence the title, derivative function, we are going to look at an actual function that will give us the slope of the tangent line really anywhere, not just at some particular location, but at any location for which it's defined. So we should note that in general, functions have slopes that change, right? And so you see in the graph here on the screen, it's just some function, maybe it's a parabola or something, call it y is f of x. And we see three different points on the graph with various tangent lines also drawn at those according points. And clearly, these tangent lines are different lines, and they have different slopes. Like right here at the top, sure looks like the slope might be 0 there. Over here on the left, that slope positive, and over here on the left, that slope is negative. So the whole idea is that, the slope changes at different points. So is there a way to describe what the slope would be at any point for a function? And that's why we want to get into the topic of the derivative function in general. So here is a picture that goes along with the graph I just showed you. And you can see that it's the same graph, but now I can just show you dynamically, okay, as we move along, right, the slope is changing. The slope of this function is changing as we move along the graph, as we can see. So we'd like to find a way to find the function that actually describes what the slope of the original function f of x actually is. So that's our goal in this video, to find the function that gives us the slope everywhere for which it's defined. So that's what we're going to do. All right. Now let's just scroll down here. What is the derivative function? Well, let's get to it. I'm going to give you a couple things to think about here on the screen, and then we are going to look at a graph. So in general, the derivative function right here, this function, notice there's this little dash looking thing right there, if you will. So that function is the derivative function. We pronounce that f prime of x, which I have written below as well. There's this other function, the derivative function f prime of x, of another function. So you kind of think we start with the function f of x. It's something like that parabola we just saw a moment ago. Then there's this other function, the derivative function of f is defined to be this limit right here. So what is it? The derivative function f prime of x is the limit as h goes to 0 of f of x plus h minus f of x divided by h. And that's, of course, provided right down here that the limit exists and the value of x is in the domain of the function f. So the function has to be defined at x, and this limit above also has to exist. Now, it looks a lot like the limit definition of the slope of a tangent line at the location a, for instance, right? If you just replace x in that limit with the variable a, then that's what we were looking at in the previous video. And that was finding the slope of a tangent line at a particular location, a comma f of a. But now what we have is that the variable x, which is the same variable that we're using as the input of the original function x. So this is any x for which the conditions are satisfied now. So what we're saying is, don't just go to some particular location a, go to any location x for which this limit exists and x is in the domain of the function, and this is how we define the slope. It's a function that gives a slope of the original function f at all locations x for which the conditions are satisfied. So let me just scroll up a little bit and write down below. You see, of course, I said this a moment ago, but when we write that notation f prime of x, the derivative function, we say f prime of x, like I've been saying. Okay, so I want to bring up a diagram here that helps illustrate what the derivative function is. So let me pull that up. All right, so what we see here is a function. Y is f of x. That's the blue function here. This kind of looks like a polynomial or something. And then we can see we got two different points on the graph. Point P is at the location x comma f of x, and point Q is at the location x plus h comma f of x plus h. All right, and then we see the green line that passes through the points P and Q on the graph of f of x. And so that's our secant line connecting the ordered pairs at x comma f of x and x plus h comma f of x plus h. Notice that the slope of this secant line is just this difference quotient right there, right? The change in the outputs on the numerator, which is the change of f of x plus h minus f of x, and then the change of the inputs over this interval in the denominator, which is just h, right? So h is just the distance from x to x plus h. And so it's very similar to how we define the alternative notation of the tangent lines in the previous video, except instead of this location x being a and this other location a plus h, we now let this location just be x. So if I let the distance h between these two locations approach 0, then of course q is going to approach p, and our slope of our secant line is going to approach the slope of the tangent line at x, right? Of course, we can go over there too, approaching from both directions. So nothing has changed in that sense. What has changed now is that this location, P, can be any x location for which the conditions are satisfied. So I can move x over here, and then if I let h go to 0 between the 2 points, again, my slope of my secant lines approach the slope of the tangent line at P, but now at a different location of x. Or I can move x over here, wherever I want. Let h go to 0. What happens? Slopes of the secant line approach the slope of the tangent line. And so you can see that what's happening now is, instead of just fixing some particular location, say at x is equal to a, now we can just find the slope of the tangent line at any value of x. And when we do that, we produce a function, f prime of x, the derivative function, defined by this limit. And what that does is it gives us the function for which at any value of x, I get the slope of the tangent line of the function f at the location x. So that is pretty much like the biggest idea that we are going to discuss here on out in the Calculus 1 discussion. Everything from here on out follows from that. Now, what does it give us? What's the interpretation? Well, clearly what we've been seeing is that it gives us the slope of the tangent line to the function f at the location x. Moreover, remember this word instantaneous rate of change, right? It also gives us that. It's equivalent to saying the slope of the tangent line. The slope of the tangent line to the function f at x is the same as telling us the instantaneous rate of change of f at x. Right? It's like a snapshot picture at that x. What's the rate of change? The instantaneous rate of change is the value of the function f prime at the location x. Now, some vocabulary. If the derivative function here, defined by the limit that we've been discussing, exists, that means the slope exists there, the instantaneous rate of change at x. And so when that happens, we say that the function is differentiable. That's just the vocabulary word describing the function, telling us that its slope is defined at the location x. As we'll see in upcoming videos, there are ways for which the slope will be undefined. That can happen. But when the slope is defined, the function is differentiable at x. And if the derivative function f prime of x exists for all values of x in an open interval, as we'll see, we always talk about differentiability over open intervals, say a to b, then we say that the function f is, go figure, differentiable over the entire interval, meaning that its slope is defined at all values between a and b. Now, one real big thing to take away here is that f prime of a and f prime of x are different things. They're very different. Now, so far, we've been using, m sub tan to denote the slope at the location a. But just notice f prime of a is really the same thing as the slope at a, right? So before we were saying, well, what's the slope of the tangent line at this location a? Well, that's just the same thing as writing f prime of a, right? Because we have that f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. It's a function that gives us the slope at the location x. If I just replace x with a, then now I'm at a particular location, whatever that x value is at a, and I can go ahead and just replace my x in the difference quotient here with a, and that will give me f of a plus h minus f of a over h. But notice that that is the same exact thing that we were using in the previous video as the alternative notation for the slope of a tangent line at a. So now, you can see that this general derivative function here, all you got to do is replace the x value with the particular number a, and we get the slope at that particular location a. And so in general, right, f prime of a, right down here, is the slope at a particular location, the ordered pair a comma f of a. It is a value. It is a number, assuming it exists. So you compare that with f prime of x. Well, f prime of x isn't a number, right? It's a function. It's a function. It has a formula. We'll find these formulas in upcoming videos. It's a formula that involves x. So a function is going to vary, unless, of course, it's a constant function. And so this gives us the slope of the original function f at all values of x for which the slope is defined. And, of course, x is in the domain of the function f. So it's a function, right? You got to actually plug in a number into x to find out what the slope is. Once I do that, I get the situation right above f prime of a. So when we write f prime of a, we mean a value, a slope at a particular location, slope of the tangent line at a. And when we write f prime of x, the derivative function, it's a function. It's going to change depending on the value of x. And that's really important to understand because a function and a value are different things in general. And so that's really it for this video. I just want to introduce this topic, the derivative function, which is a big topic conceptually. And so in the upcoming videos, we're going to look at, let's go and find some of these, right? Let's go ahead and find f prime of x for some value, or sorry, some function f, and then we'll also introduce even more notation to describe the derivative function. And then we'll start looking at how derivatives can be undefined versus defined and whatnot. A lot of things still to come, and eventually the goal is to come up with the formulas for f prime of x, really for any single variable function that we can imagine. So hopefully that helped you get an idea what a derivative is, a derivative function of a single variable function. And until next time, it's Math and Beats, and I'm out.